ladies and gentlemen. So let me start with the first lecture, the first race through the slides. It's this kind also of driving experience. So this morning I would like to tell you something about the analysis of DOCSIS 3.1 signals on the physical layer. So nowadays DOCSIS 3.1 is a subject which is considered by several network operators, by manufacturers of components, network components. But maybe you have heard something already in theory, but we've never seen any examples of the signal based on measurement screens and so on. My lecture is divided in two parts. As a kind of warm-up, I will start with the question, why DOCSIS 3.1? And of course I will give you also some answers on this question. Then I will continue with the introduction of the characteristics of DOCSIS 3.1 signals, mainly on the downstream. And I will do this in this way so that I will explain step by step the parameters of a DOCSIS 3.1 signal, and I will give you some ideas how the parameters can be measured. And also in addition I have implemented in my presentation some measurement examples so that you will get a first impression about the DOCSIS 3.1 signals. Why DOCSIS 3.1? So it's no secret, of course, more and more the people are used to watch TV or video content via IP passes or transmission passes. The people would like to see, let me say, TV sets, television sets via video on demand, via YouTube and so on. But also in addition, so new technologies came up and so which drives the quality of the video content, 4K for example, or UHD video as a name for that. And of course also in addition, so the people are using more and more cloud services from different players, of course, to download or upload photos and photographs and other data. But every service needs bandwidth in the networks, so independing who the IP data are delivered. So typically, so the providers are ADSL providers, which gives the IP data via LTE, for example, and via satellite. But fortunately, so cable network operators have a very good position in this race. And so as you have the connection to the homes, of course, you can nowadays also already provide high bit rates, of course, but in the future the demands will increase. And the demand for higher bandwidths will be more and more also within the next years. So you can find nowadays also a mixture of network infrastructure. So nowadays we have fiber already in your networks, but most of the time so there's still a piece of copper, a coax cable to the customers, which must be bridged. And for that, of course, so we have the DOCSIS 3.0 developed and in operation, but facing the demands for the higher bandwidths, of course, we have to find a new solution to provide more and more bandwidth to the customers, and the solution was found in DOCSIS 3.1. So the good thing is, of course, that DOCSIS 3.1 works together with the nowadays standards 3.0, which I think so is very important because in this way cable network operators have the possibility to make a rollout without any serious impact to the nowadays customers. So let me start with the first slide, which gives you a first impression about DOCSIS 3.1. So with DVB-C, for example, J83B or DOCSIS 3.0, so we have so-called single carrier standards or in use, or single carrier modulation in use. But now with DOCSIS 3.1, so OFDM is now the new technology in the cable networks. OFDM means we have here thousands of carriers in use, filled up to bandwidths up to 192 megahertz. And for that, so several transmission modes are defined depending on your capacity needs in the cable and so on. So if you have a look to the downstream, so you can select different modes. One mode will be the 4K mode. That means we have up to 4,960 carriers which are modulated in different ways, and so up to more than 8,000 carriers in the downstream. And in the upstream, one can select between 2,000 carriers, roughly up to 4,000 carriers. And what does it mean, OFDM? So hopefully it works. So it means we have here the thousands of carriers in parallel. So here we will see the frequency, and then we have the time axis and so transmitting the data. And here you can see already the first parameter, the bandwidth, which can be in the downstream up to 192 megahertz. So it's amazing, of course, but it sounds it's in the first step very complicated, but it's not so complicated. So in this slide, so I try now to explain you step by step the technology behind. So this picture shows the carriers or the frequency, also on the oops, sorry, that was the wrong one. Is x-axis, and here all the carriers. And the carriers, that's an interesting thing, can be modulated in different styles. So in the downstream, you can modulate the carriers from 16 QAM on up to 4,000 QAM. So it's amazing. And based on the DOCSIS standard here, DOCSIS 3.1 standard, already in the specification you can find also constellations with 8,000, more than 8,000 fields, up to 16K QAM modulation. But I think so it will be more the case in optical fiber networks, of course. To transmit this on copper would be a very big challenge. In the upstream, so we start much lower, so with PSK modulation up to 4K QAM. And simulations can be done in a different way. It's not necessary, of course, to modulate each of the carriers in the same way. So it means you can here select a group which is modulated maybe with 256 QAM, and so another group can have the nice 4K modulation order. And if we are using different modulations, so we are talking about profiles with the new standard, so there's a possibility to define up to 16 profiles in the downstream and up to 7 profiles in the in the downstream and the upstream, up to 7 different profiles. And the meaning is so that the profiles can be chosen for different conditions of the network. So if you have bad conditions, of course, you will select a modulation scheme on the lower end. And if you have very good conditions, very good carrier to noise ratios, for example, then you will have higher QAM orders in your network. Next slide is quite or slightly more complicated. So, but it's necessary to explain you some additional parameters. So we have here the carriers again in the x-axis, and here you can see now all the carriers. And the carriers are modulated in a dedicated way. So you have for a dedicated time the symbols which must be transmitted, and the group of symbols are, let me say, collected to an OFDM symbol. All carriers are transmitted always in parallel, and that means so if you transmit all the carriers in parallel, then we are talking about OFDM symbol. And in addition, so we have here on the next axis here, axis the time axis, and also symbol numbers. And the symbols, OFDM symbols, are transmitted in a certain distance of time. So then we are talking about symbol duration, and up to 128 symbols in total. And then we are talking about an OFDM frame in this way. And then afterwards, so after a frame, so the symbols are counted again from null until 127. It's important to know, of course, the symbol duration, because from the symbol duration on, we can calculate the channel or subcarrier spacing. That means we have here in the 4K mode or 8K mode 20 microseconds and 40 microseconds. And the resulting carrier space is now 50 kilohertz between all the carriers, or otherwise 25 kilohertz. So I talked already about the bandwidth of a downstream signal. So the bandwidths can be in the downstream between 24 megahertz and up to 192 megahertz. And in the upstream, we have to consider the 4K mode or 8K mode. It starts from 6.4 megahertz or 10 megahertz up to 96 megahertz in the upstream. And if you are talking about bandwidth, it's also an interesting thing, because we have to consider a certain sampling rate in the downstream, which is by 204.8 megahertz. And here you can see, of course, that by the transmission, not all carriers are used or for data and other things. So we have here defined certain guard bands on the lower end and the upper end. And here in the middle, you can see the group of used carriers, and with 192 megahertz. So we have here 3,800 subcarriers in use, in this case with a channel spacing of 50 kilohertz, which results in a bandwidth, in real bandwidth of 190 megahertz. So if you define, or if you talk about a channel bandwidth of 192 megahertz, so the real spectrum is in real 190 megahertz based on the guard bands. That means if you place another DOCSIS 3.1 channel on top or on the lower end, in a distance of 192 megahertz, you will have always a gap of 2 megahertz, which is the minimum which is defined in the standard, to be sure that the channels don't interfere to each other. So in the following examples, I did the measurements with two devices from our company. So on the left side, you will find a channel generator, cable load generator for DOCSIS, which is able to simulate a complete channel frequency plan. So with analog signals, digital signals, and on top here in this example, also with a DOCSIS 3.1 signal. And on the other end, we have used for the measurements one of our spectrum analyzers, the FSW, together with a piece of software which enables the spectrum analyzer for the analysis of DOCSIS 3.1 signals in downstream and upstream. So the simplest measurement which could be done is at first the spectrum. So I have selected for this example a 4K mode with 192 megahertz bandwidth, nominal bandwidth, 3,800 carriers, subcarriers are in use. And here sometimes you can see it here also the setting from the generator, so as a reference. So a typical OFDM spectrum has very sharp edges and a very clear spectrum if nothing happened with the signal. And so, but it's a typical characteristic if you have a comparison with the QAM signals, nowadays DVB-C signals, of course. So the edges are rounded, and here, based on this, of course, you have always very sharp edges. Then the next measurement was done also on the spectrum side, but here I have selected the occupied bandwidth measurement of the spectrum analyzer, and to show you the occupied bandwidth. And the spectrum analyzer gives just the possibility to define a channel power, let me say, density of 99%. And the resulting bandwidth was then in this measurement 188 megahertz. But if you calculate it with 100%, so you will end by the 190 megahertz income-based spectrum. And you can see it here also on the left side, the setting of the generator. It's also one interesting thing, because by the frequency you cannot see the value for the center frequency. You will see it here. It's defined, the frequency is defined on the carrier null. That means if you place the channels in your cable network, you have always to count from the carrier null of the up to 4,000 or 8,000 carriers if you place the channel. Then the next slide explains a new term. So it's the cyclic prefix, which is defined to deal with microreflections, which is, of course, sometimes the case in your networks. So for that, we are doing a little trick in this standard, which is not brand new. So if you a little bit heard about DVB-T, DVB-T2, for example, of these standards, they're using the same method to dealing with echoes. So here you can see it here now, for example, a signal. So here I talked about some symbols. You can see it here now, the different symbols which are transmitted over the time. But based on the reflections you will receive, or the modem will receive, also the same symbols, but with some delays based on the reflections. And without any measures, of course, we would have simple interference, which reduces the MER values, of course, gives bit error rates and so on. But with a little trick, you can avoid it. So the trick is done in this way, that from the symbols, a certain part will be copied and moved to the beginning of the symbols. And in this way, so we have defined a certain, let me say, range of time where the receiver can do something by a correlation. So that means it can compensate a certain amount of echoes and so. And for the cyclic prefix, so in the standard, we have several possibilities. That means if you select, for example, 5 microseconds, then you can deal with microreflections up to 5 microseconds, so without any really serious problems. But the disadvantage is, so if you define high values for the cyclic prefix, you will lose bandwidth. And so it's always a certain compromise depending also about depending on your conditions in your network, for example. So I did here an example, so to show you the different effects of the reflections. With the generator, so I have generated a delay of 3 microseconds, and the cyclic prefix was defined by 3.75 microseconds. And here on top you can see the results without any reflections, so we are in a range of 50 dBs. And with a delay of 3 microseconds, which are within the cyclic prefix, so the degradation of MER was not dramatical. So it was just by roughly 2 dB or less than 2 dB. And here I did send, or have generated a reflection of 5 microseconds, which is outside the cyclic prefix. And you can see here huge degradation of the MER, for example. So just to show you the effect and the influence of the cyclic prefix definition. Then frequency ranges. It's also a very interesting subject, and besides the technology of DOCSIS 3.1, I think so the frequency plan will generate a lot of discussions by the network operators. Because depending on the frequency plan, there's also a certain strategy of your network operator, of the network operators behind. So on top you can see here nowadays spectrum, so it starts in the upstream from 5 megahertz up to 47 or slightly higher. We have here still analog channels inside, we have here digital TV inside, and so which could be transmitted up to 1 gig roughly, but I think so the highest frequencies nowadays are at 862 megahertz most of the time. In the line 2 you can see maybe the first scenario of the rollout of DOCSIS 3.1. So it's said, or there are some ideas to place the first downstream channel on top of the legacy channels here. In this way, of course, you can roll out DOCSIS 3.1 without any serious impact to the existing channels. And maybe in the next steps then, you have to switch off the traditional channels, of course. You have skip analog TV and maybe other services, step by step. So it's the intention to fill up the spectrum with the DOCSIS 3.1 signals in the downstream. And you can see it here now, based on the DOCSIS standard, the frequencies are defined up to 1.8 gig roughly. So you will see, as currently, so most of the network operators are fighting for the frequency extension to 1 gig, and think so nowadays it's already challenging. And so based on new amplifiers and so on. And with DOCSIS 3.1, so it's also defined here a new frequency border between upstream and downstream. So it could be by 107 megahertz, for example, or or by 85, and can be increased to 117 or 204 megahertz if you're using the complete spectrum up to 1.8 gig. So if you have a look to the channel plan and to the numbers of channels, so you can fill up the spectrum very in a high density, but then you must be aware so that the channels don't interfere to each other. And to avoid this, so by OFDM, so we have also also by DVB-C, a kind of roll-off or filtering. And the filtering can be done also with different values for the filtering, from a low filtering to a high filtering. And you can see here the different effects of the filtering. So if you are using a very low value for the filtering, so you would have a wide spectrum. If you do the filtering with the higher values, of course, the spectrum would be sharper and the edges would be sharper, and the influence to the neighborhood channels or adjacent channels would be lower. And here, a very important rule. I talked about the cyclic prefix before, so to dealing with microreflections. So if you define the filtering, of course, the value of the filtering must be always lower than the cyclic prefix. In this example, so I did two measurements. On top, you can see the measurement or the spectrum with a high roll-off filtering. So you can see the sharp edges and so, and the spectrum here is very, very steep. And so, and below, I have reduced the filtering, and here it's not so clear, but you can see, of course, the spectrum is slightly wider. And so, to show you the effect of the filtering. On the next slide, so I did something extremely. I switched off the filtering to show you the effects without any roll-off. And I have used for this example, or for these examples, the measurement MER versus carriers. It's my favorite of the measurements, especially in connection with OFDM, because this measurement shows the MER value for each of the thousands of carriers. And in this case, in this way, you can see very precisely any influence to your signal. And here you can see now the spectrum without any filtering and so on. You can see it here now, the spectrums of the left and right channel smears a little bit to each other. And it can be seen by the MER over the frequency on the both slides here. So you can see it here now, the MERs here are pretty high, but it will be degraded to the middle or to the edges where the channels are influenced to each other. And if I switch on the filtering, of course, the MER values looks good, and so and flat. So this is a good example, of course, to show you how the filtering and the roll-off will works. And here by the MER to the where the carrier measurements, here you can see here in this case it looks a little different maybe, or a little bit interesting. You can see here the values in several colors. Yellow means, of course, we are measuring the minimum MER from time to time. So the blue curve means the averaged MER values, and then the green ones means the maximum MER values for each of the carriers. And here you can see a lot of peaks. It's not a fault of the measurements itself. It comes from pilots, which will be explained some slides later on. Here, some slides means one slide. So, together with the standard here, OFDM, so it's also common to talk about pilots. It's not new, it's also used by DVB-T2, for example. So the pilots are very useful and have different, let me say, tasks within the signal. So we have to decide between two kinds of pilots. We have continuous pilots and continual pilots and scattered pilots. What does it mean? Here, meanwhile, the very known drawing of the subcarriers here. So it could be here carriers or frequency, and the OFDM symbols again. And here you can see it here now, so that we have on dedicated positions continual pilots. So it means continual means, so if the OFDM symbols are transmitted, the pilots have always the same location. And then, in contrast to the continual pilots, we have the scattered pilots, which are traveling from symbol to carrier. So it's like a sweep of a spectrum analyzer. So, and the purpose of the carriers is a little bit different. For the continuous type pilots, so the continuous pilot should help a cable modem, for example, for the synchronization in frequency and phase. It's the first purpose. And the scattered pilots should help to make a kind of channel estimation regarding the frequency response. It should help the equalizer to make the spectrum flat as good as possible. So here also one of my second favorite measurement. This measurement is similar to MER over frequency, but here in contrast we have in addition information. So we have here the x-axis, so which counts the carriers of the signal, And here you have now the symbols, so that means the time will start here and will continue up to 128 symbols or 127 symbols, because the symbol 0 counts also to the 128 symbols. And here you can see now on these examples the continual pilots, which have always the same position during the transmission. And here, in contrast, you can see the scattered pilots, which are switching always a position from symbol to symbol. And so, in this way, it can be very nice explained, so how the symbols and carriers are used. And the color of the symbols here gives an indication about the MER. So it is a very nice measurement here, because we have here not only the information about the MER values over the carriers, you have also in addition the information about the quality over the time. So it's sometimes useful if you are dealing with some problems and some troubles. So from the pilots, so I have here in this example 48 continuous pilots, and so which can be, I go back to the other slide, so it can be, the density of the pilots can be increased up to 128 pilots, continual pilots, but always with a disadvantage. So if you select a continual pilot, so it's not anymore, let me say, available for the data. So it's always a compromise, so you can define the signals very robust, but versus bandwidth. It's a golden rule, or it's physics. Then, before you have seen by the MER over frequency, nice peaks in the measurement. And where do the peaks come? So the peaks come from the pilots. We heard it before, but I have missed some information. Here you can see it here, the pilots are modulated with a higher power, 6 dB higher than the rest of the carriers. So, and therefore you can see it here now in the power spectrum measurement. Here's the peaks, so we have here the data carriers, and here in between all the pilots which are powered 6 dB higher. And so it can be clearly seen. And in this example, I did set up the generator with a 15 dB tilt via 1 gig, and which results more or less by a bandwidth of 200 megahertz to a tilt of 3 dB. And so, and you can see it here, of course, this analyzer had no problems to dealing with the tilt based on the pilots and so, and the equalization of the frequency response. And here in addition, we have here also some measurement informations about the signals in detail. And you can see it here, the power of the data carriers is a reference with null dB. And here the power of scattered pilots and continual pilots are increased to about 6 dB. So it means here you can measure directly the quality of the modulator. Okay, always some detail I missed. So here in the middle, you can see a group of pilots. It's interesting. So normally we have here more or less equal distances, but here in the middle, you can see a group of pilots. Why is that the case? So a new parameter by DOCSIS 3.1 is now the PLC. So it means a physical layer link channel is defined, which gives the modem the information about the modulation schemes and so the different profiles which are used. And the PLC has to be located on a clear spectrum. So it's recommended because the PLC is a very important carries a very important information for the cable modem. And if you locate a PLC on a frequency which is disturbed or interfered by another kind of signals, of course, so that could cause some trouble. And the PLC is defined, or the content of the PLC is defined by the CMTS. So it gives the modem the physical information. And the PLC has a frequency range of 6 megahertz. And so it's similar it comes from the States based on the channel plan which is used in the States. So PLC, a little bit more in detail. So the PLC carriers can be modulated in different modulation schemes. The most robust one is the PSK. It can be modulated up to 16 QAM. And in detail, so you can see it here now, the carriers. The carriers have a kind of preamble to make a synchronization easier for the modem, and followed by up to 120 symbols, so which carries the data about the profiles, modulation schemes, and so on. and important to know, so the channel bandwidth is defined by 6 megahertz, but just a small portion of the 6 megahertz is in use for the carriers, and so protected by a number of continual pilots. And important to know, of course, so that the location of the 6 megahertz channel must be always on a 1 megahertz grid. So to make it easier for the modems to make a channel scan and to find the PLC information which is necessary afterwards to have the following informations for the complete decoding of the signal. Depending on the 4K mode, or depending on the 4K mode or 8K mode, we are dealing with, in one hand, 8 carriers for the PLC information, or up to 16 carriers in the 8K mode. So back to my favorite measurement. So here in this case, I zoomed in the power spectrum measurement to show you a little bit more in detail all the continual pilots around the PLC information. And below you can see again the measurement MER versus carriers or symbols. And I zoomed in also here in the first step and zoomed in a very high detail. And here you can see the carrier numbers here, and based on the generator, so the PLC information is located by the carrier 2104, which is also indicated by a marker which is placed here. It's not so clear, but here you can see it. And here you can see the group of the 8 PLC carriers according to the 4K mode. And here is numbers of continual pilots which protects the PLC information. So I introduced at the beginning the possibility to define several profiles for the transmission. So the profiles can be modulated in different modulation schemes. And what is the purpose of it? So here, for example, I catched the curve from Cable Labs. So we have done some investigations on modems and also on cable networks to show the distribution of quality in the networks. And so it means most of the time, so we have a performance, MER performance in range of 38, 39 dB. In some cases, of course, you have to dealing with very, let me say, bad conditions, or sometimes you have also very good conditions up to 44 dB, but it's very seldom. And depending on the quality, so there's a nice idea to, let me say, to make an agreement between the CMTS and the cable modem, depending on the quality of the transmission path, to select one of the defined profiles. So a cable modem must at least dealing with up to 4 profiles in the downstream, and so I think so 2 profiles in the upstream. And so depending on the quality, of course, so the profiles will be assigned to the modems. It could be done in a different way. But the most important thing is also the profile A has to be, let me say, defined in the most robust style, because profile A must be received from a cable modem by a cable modem in any case. Because in profile A, there will be also some additional information which are necessary to dealing with all the other data and other profiles. And if we have now several profiles in the signal, so we have to tell the modem also where the profile starts and where the profiles end. And for that, so we have here a new parameter. It's named next code word pointer, which points directly to the different portions of the signal. It can be seen on the next slide, but here also to mention, of course, so that the next code word pointer can be modulated also in different modulation schemes, and so up to 64 QAM. So this slide looks in the first step a little bit complicated, but it shows nearly the same as before. So we have here the carriers, and here we have here the symbols. That means also symbols means transmitted over the time. We have here the time axis. And so here you can see now here so that some carriers are defined as next code word pointer symbols or carriers, which points to the several portions of the signal. So that means during the transmission, we have maybe 1, 2, 3, 4 profiles in the transmission, and with the different lengths. And depending on the, let me say, request for data, bit rate, and so on, and quality, So the different profiles can be assigned, and the modem knows both based on the next codeword pointer where the several portions can be found in the signal. So, but it's important to know, of course, for the modem where the next codeword pointer information is. So how does it look like on a test and measurement equipment? So here an example from the analyzer, which gives you a table and which shows you now in detail the distribution of the carriers to the different profiles. So here we have the different profiles. So by the generator, 4 profiles were defined. You can see it here. Profile A was in the most robust modulation defined, up to a profile of 4K. And here you can see now the subcarriers and symbols, of course, and the information from which carrier to from which symbol the different profiles are distributed within the signal. And resulting this, of course, or as a result, you can get also a measurement table which gives you some more details about the quality of the several portions of the signal. So from the pilots, so PLC preamble was explained before, PLC data, so over the next codeword pointer, and here also with dedicated MER values for the different profiles which were described here. You can see it here again, 16 QAM up to 4K QAM was implemented in the signal. Then here some constellation diagrams. So I think so you are used to work with constellation diagrams for DVB-C or for J8CB. But now we have here in the signals much more information, so based on the several portions of the signal. So here you can see the definition again with the different profiles, and also here's the definition of the next codeword pointer, which were modulated in QPSK. And here you can see now the boosted pilots only, so which are 6 dB higher as the rest of the carriers. And so you can see the PLC constellation, which is always 16 QAM modulated. And here you can see the modulation of the next codeword pointers according to the QPSK modulation. Next slide gives you more profiles and constellation diagrams. So starting from the simplest one, profile A, up to the profile C, which is defined with 4K. So it's already an amazing constellation. And here profile D is modulated also in a very interesting modulation scheme. It's a combination between 128 and 256 QM. And so it's also defined, of course, to have a little bit smaller steps between the constellations, because normally if you are using the next step of constellation, so you have 4 times more symbols in your constellation. So that means you have to boost your signal level by 6 dB, or you must have 6 dB higher carrier to noise. But this combination of constellations gives you the possibility just to make a step by roughly 3 dB averaged. It's also defined or developed with a new standard. This constellation, of course, gives the summary of all content of a DOCSIS 3.1 signal. And so, fortunately, so it's different in color, so that you can still see some details of the signal. And so at the beginning, we have started with just one color, and so it was impossible to see the details in the signal. So it was a next evolution step by our measurement equipment. So next part, which should be explained, is the interesting thing, exclusion band. So exclusion band, so what does it mean? So with the DOCSIS 3.1 standard, so it's now possible to define some ranges where the carriers can be switched off. And so why? So sometimes you have to deal with some interference with other signals. So there's a possibility to switch off some carriers to avoid some serious problems. But sometimes it's also possible to switch off dedicated carriers to avoid any problems with ATC signals or other signals, LTE, whatever, which maybe interferes with your network or vice versa. And so exclusion bandwidth offers different possibilities. It's important to know so that the exclusion band, the bandwidth of the exclusion band, is not allowed to be smaller than 1 megahertz. So, and in total, not more than 20% of the spectrum should be switched off. Make also no sense, of course. You would lose, of course, a lot of bandwidth. So here I did an example to show you the advantage of exclusion bands. So here you can see as a regular spectrum as seen at the beginning, but here the difference is, of course, we have one interferer in the background. So I show here the spectrum just from the interferer, and afterwards I have overlaid it again. And the disadvantage of the spectrum is, of course, nobody can see really what kind of interferers are behind, as long as the interferers are in the level lower than the used signal itself. But I come back to my favorite number one of the measurement screens. With the measurement MER over frequency, you have a very nice possibility to detect all the interferers in the background of your signal. Why? So I told you, you can see here the MER value for each of the carriers, but here now we can see it here by the interferers. So on some carriers, so we have a huge of impact, and in this case the MER over frequency is in this case a kind of spectrum analyzer, which gives you the spectrum of the interferers, also in a kind of mirrored spectrum. So it means here the interferer with the highest level reduces also here on this position the MER to the lowest value. And it's very useful. And in addition, of course, you would be faced with a number of bit errors, which appears based on the impacted carriers. But thanks to LDBC, which is now also, let me say, used, the powerful forward error correction in connection with DOCSIS 3.1, so the bit errors can be corrected. As in this case, it's not a serious problem, and so, but you can see it here, the impact of the interferers. And what I did in the next slide is to, let me say, to detect the position of the interferers in this way. So I have used the marker function in this measurement screen here, and I have defined a certain range, so where the interferers are in between. And so you can see it here, it starts by carrier, I have to look at here, by 2,500, something like that. And the second marker is at a distance of 192 carriers away from the first carrier. It's the information which is useful then afterwards to define the exclusion band by the generator. I did it here over there, of course it's not clear. So I start again by the carrier 2570 to get, and have defined the bandwidth with 192 carriers and switched off the carriers then afterwards. And you can see it here now in the MER over frequency measurement here, the gap which is now defined by the exclusion band. And so it looks good. Disadvantage, of course, loss of bandwidth, but you are not faced anymore with the bit error rates. It can be seen on the next slide. So the bit errors are to zero, decreased to zero. And here you can see on top the frequency spectrum with the switched off carriers. And here just in the middle you can see still the peaks of the interfering signal. Last slide, hopefully I'm more or less in time. So it's a measurement, it's called CCDF. So it means complementary cumulative distribution function. It sounds complicated, but I think so it's also important to know the characteristics of the OFDM spectrum. So how will it be leveled in your network? What does it mean? So maybe you know it already, the measurement, or maybe it's unknown. So this curve shows the distribution of the different levels over the time, which can be happen or could be seen on an OFDM signal, or in this case DOCSIS 3.1. And on the left border, you can see here the averaged value of the level over the time. And here you can see the distribution of the peak levels over the time. And so with a certain probability, and of course the highest peak levels will be reached with a very low probability, but it can be. And so if you have to design the leveling, if you have to calculate certain headrooms and margins in the network, then you have to deal with some value. It's called crest factor, which explains or which gives us information just by the difference between the averaged value and the highest peak value. So that means so you have to level your signal roughly 10, 11 dB lower, of course, away from the critical point, so for laser clipping and so on. And here, in contrast, I did the same measurement with a DVB-C channel, And so you can see it here, the guest factor was by roughly, I think so 9 something dB, and so slightly lower than of the OFDM channel. Should give you just a number and the right feeling. So if you have to calculate your networks and if you have to optimize the leveling. That brings me to my last slide. So hopefully you got the first impression about the OFDM signals, a little bit more from the practical side. DOCSIS 3.1 seems slightly more complex. It is compared to QAM signals nowadays. And so, but based on the complexibility, DOCSIS 3.1 offers you also more possibilities for the optimization of your network and to squeezing, let me say, your nowadays infrastructure for the highest bit rates which are possible with a piece of copper inside. And the good thing is, of course, also that with the right analyst tools, you can dealing with the different parameters, you can dealing with the different effects on the signal. And so that I'm optimistic that we at the end be able to manage DOCSIS 3.1 in the networks. The slides have shown most of the time examples from the downstream. So upstream is another story. It's let me say to 80% similar to the characteristics, the measurements on the downstream, but by the upstream, of course, then we have to also to dealing with other effects and so bursted signals and so on. But maybe it's part of the next lecture, maybe in spring or whenever. And so, but here I would say I'm finished now with the first race of the day. And hopefully it was so far useful for you, of course, to get the first impression. Thank you.